sinuses are filled up. Okay, now we'll go from current slide.
At the end of chapter 3, so you're going to have to give us another test.
Yes.
Gee, hey.
What a joyous weekend you have ahead, right? All right, we're at the top of page 132, chapter 3, section 3.4, area, volume, and equations of lines and planes. These are just applications of determinants. That's the title of this section. Earlier we were looking at Cramer's rule, how to solve systems of equations using that. So let's look at area of a triangle in the xy plane. So here we have, actually I think I'll go, oops, to this, okay?
There's a proof.
What's that?
I said, there's a proof.
Yeah. Let's say we have a triangle.
Oh, turn on the projector.
Oh, I'm sorry, I forgot. I thought I hit that.
I think it made noise.
Okay, there it goes. All right.
Just save it.
Let's say we have a triangle. Let me get my pen activated. Okay. Say at x1, y1, I hope I'm choosing this wisely, x2, y2, and x3, y3. Probably is not going to be the best choice, but we'll go with that. Okay, here is a triangle, somewhatly. Okay, now here's what the theory says. This is what the area of a triangle xy plane. The area of this triangle, area, is equal to, though probably I should put at least AR, because everything has been A so far. Area is equal to 1/2, interestingly, the determinant of this, and this is in the xy plane now, x1, y1, 1, x2, y2, 1, x3, y3, 1. Those coordinates done like that.
So where does the 1 come?
Oh, I'm sorry. I left off something. Plus or minus. Okay. Let me clean this up just a little bit. Hit the wrong button. Okay.
So,
all right.
Again, where do the 1s come from?
They're just there. Okay.
Because
Yeah.
I don't know, just because we've been working in 3 dimensions in
Right.
another class, I want to say that, like, it's kind of saying
It's
everything is
floating
all on the same plane as
Right.
far as Z,
Yeah.
but I don't know if that's
No, it just happens to work out this way. And maybe in the proof we'll see why that's true. All right. Now, that is what the area is. Voila, here it is. The plus or minus sign is chosen to give a positive area because you can't have a negative area. So you choose whichever one. If the determinant's negative, choose the positive. Choose the negative. If the determinant's positive, ignore the negative. Okay. Now, what we're going to do is proving the case for yi greater than 0. So my picture doesn't do justice. So let me change my picture. Okay. I probably will regret this, but let's do it here. Let's do this as x3, y3. There's your triangle.
positive.
Yeah. All the y's have to be positive. X's don't have to be, but the y's do. Now, they're assuming that x sub 1 is less than yeah, there it is less than or equal to x3, and x3 is less than or equal to x2. So I got that right. Huh? Amazing. Okay. Above the line segment connecting x1, and that y3 lies above the line segment connecting x1, y1, and x2, y2. Got it again. Okay. Now, let's consider the three trapezoids whose vertices are, and they did it in red, so let's do it in red just for funsies. There's one. There's one. Now these aren't trapezoids, those are lines, but they define a trapezoid. Okay. Here's the first trapezoid, there's the second trapezoid, and here's the third trapezoid. Okay. Now, what we're going to do is the area of each trapezoid. What is the area of the first one here? You remember the area for a trapezoid? Here's I can't really do it. I can wave my arms to do it. Let's take this trapezoid and flip it up here.
Oh, yeah.
And you get a rectangle. Right? Which is exactly twice the area of that trapezoid. Yeah. So you do this base plus this base times that height, they used to call it, and take half of it. Okay? Because this base plus this base will give you the length of the rectangle, right? Mm-hmm. And so times this would be the area of the rectangle, take half of it, you get the trapezoid. Okay? So, okay. So that would be, let me go back to black then. Okay. The area, this will be T1. This will be T2. And this one down here will be T3. Okay. So the area of that first trapezoid would be 1/2 x1 plus x3 times y3 minus y1. No, I've got those backwards. These are y's and those are x's. Sorry about that. Goodness gracious. Okay, these are the y's, these are the x's. Duh. What's that?
The order probably doesn't matter.
Well, yeah, but one's a plus and one's a minus.
Yeah,
this is y1 plus y3 times the difference in x3 and x1. Okay. That's area of trapezoid 1. Plus the area of trapezoid 2, which is 1/2 of y3 plus y2 times x2 minus x3. Okay. Then minus trapezoid 3, which would be 1/2 x1, no, y, I keep wanting to say x, y1 plus y2 times x2 minus x1. Okay. Obviously a 1/2 comes out front. Okay. Now let's do some of those foilings, okay? This would be x3 y1 minus x1 y1 plus x3 y3 minus x1 y3, right? Plus x2 y3 minus x3 y3 plus x2, y2 minus x3, y2 minus x2, y1 plus x1, y1 minus x2, y2 minus plus x1, y2. Okay. Now let's see if we've got anything that disappears here. Those go. The x1, y1s, there's a minus at the beginning and a plus near the end. I'm not sure they should, but it looks like they're going. x3, y1s. I don't see but one of those. x3, y3.
There's 2 of those, plus and minus.
Yeah, plus and minus of those. x1, y3. I think there's only one of those. x2, y3s. Only one of those. x2, y2s.
There's 2 of those.
Yeah, and one's plus and one's minus. And then we have x2, y1s.
That's all that's left. Everything else is
Yeah.
left over, I think.
Okay.
And
Now, let's see what our determinant of that thing is. There's the 1/2 out in front. Determinant of this thing, if we chose, now do you have a preference on which you might like to choose
preference of what?
to do your determinant of the matrix? I take that column of ones.
Okay, you're
Okay.
you're talking about the original.
Determinant.
Yeah, that matrix.
Right, of that matrix, yeah. That would be x2, y3 minus x3, y2. x2, y3 minus x3, y2. There it is. Okay? Minus, that's a plus position. This is a minus position. Minus, let me clear my crosses here. Minus x1, y3 plus x3, y1. There's a plus x3, y1 minus x1, y3. Okay? I'll clear those off so it'll be easier to see what we're talking about. And the last one would be plus x1, y3.
Y2, you mean?
Yeah, x1, y2, sorry.
Minus X.
There it is, x1, y2 minus x2, y1.
That's
Sure enough, that's it.
And 1/2 out front.
And with a 1/2 out front, exactly. So sure enough, that works. So, at least when your y's are all positive and your x's are in that order. If they're not, shift your, yeah, make sure it is. Okay. All right. In fact, I think what they do is always say in the first quadrant. And then whenever you're in the first quadrant, do your order so that your x1's less than x3's less than x2. Okay, if you are in the first quadrant. Okay, so let's do, and we won't need, well, we might need, so let's just clear this. Okay. Find the area of the triangle whose vertices are 1, 0, 2, 2, 4, 3. I think you see we have a problem, don't we?
Well, hold on.
But let's do them. 1/2 the determinant
So we have a
of,
problem.
well, never mind. That's a 1, 0, 1, 2, 2, 1, and a 4, 3, 1. Okay, it's going to be plus or minus that. This will be area. Okay, so let's see what we get. Plus or minus 1/2 times. Now, I just like to do my times the other way.
I said we use that first row.
You like the first row?
Yeah.
Yeah, I do too. I just did the other one because there were no zeros.
If you wanted to, you could do a column 3 minus column 1, or negative column 3 plus column 1, and get it 0, 0, 1.
Okay, you want to do that first? Okay, so
Be 0, 1, 3 for the first column.
okay,
0, 2, 3.
0. Wait. You said
Negative 1 times column 3 plus column 1.
okay. So that would then be, yeah, that would be a 0. That would be a 0, and that stays a 1, right?
Yeah,
Oh, you're going down again. Okay, I was going to see. That would be a 1, and that would be a 3. This would be a 2, and a 3, and a 1, and a 1. Okay. All right. Doing that, plus or minus 1/2 times. Take the 1 times.
That would be 6 minus 6, which is 0. Right? Oh, wait, sorry, I wrote a 2 there. My bad.
Okay. It's supposed to equal 0. What have we done wrong here?
It's supposed to equal 0?
Yeah, it is.
Negative 1 plus 1 is 0. Negative 1 plus 2 is 1. Wait, can we not do column operations?
We can with determinants. But
That should be 3 minus 6, which is negative 3.
yeah, that ain't supposed to be what we get. Let's see if we did it without doing the change, what we get. That would be 2 minus 3 is a minus 1, and this would be, did I copy the thing wrong?
I
No.
was just going to check that.
Okay. That would be a 6 minus 8 is minus 2. That gives us a minus 3 also. I mean, minus 3/2. Oh, wait. I was looking at the thing on the next page. I'm sorry. I was looking at the thing on the next page.
For something else that's not.
Yes, sorry about that.
Okay.
I plotted the points wrong. Okay. Let me do my eraser. It's 1, 0, not 0, 1. Okay. No, we did, that was right, this was wrong. Okay, sorry about that. We calculated correctly. It was 1, 0, but I was looking at the next page. There's 1, 0. Here is the triangle we're doing now. Okay, and that does give you, either way you did it,
Negative 3 there.
that was a negative 3, so this would be 3/2, and that's the area, and that's what we got before too. Okay, so 3/2 square units. Then they said, what if we had chosen this point, 0, 1, rather than 1, 0? Okay, then we'd have had the area of that one to be, I'm sorry, I was looking at the wrong page. plus or minus 1/2 times 0, 1, 1, 2, 2, 1, 4, 3, 1, okay? And then we would do plus or minus 1/2. And this time I'm assuming you would
add negative row 3 to, or column 3 to column 2.
Right, that would be a 0, 1, 2, 1, 1, 1, okay? And then when you did this one, you get 4 minus 4 is 0. So if you get a determinant of 0, that means the area of 0. In this case, that means you gotta be collinear.
It's a line.
Yeah, I caught a line, exactly. And that would be collinear. Okay, I'm sorry, I was looking at the graph of the next page thinking that was the graph of this one, because all they did was switch those two on me.
Yeah, very similar.
Now, which then leads to another application that if you have 3 points,
and you take the determinant in 0, you know it's a line.
then you know those are collinear. And that's the only way they can be collinear. If that determinant is not 0, they're not collinear.
So if there was a question that said, are point A, B, and C on the same line, you could throw it in matrix C.
Right.
Or matrix and find out if they are.
Yeah, exactly. Yes, exactly. So,
that is awesome, because I'm pretty sure those questions come from other places too.
right,
But
right.
usually they only give you 2 points, not 3.
Right, right. Wait, any 2 points are collinear.
Well,
They'd have to give you 3.
it would be, or if the point is on the graph or something.
Right. Okay. So,
And you could just
if you had it,
on that graph.
yeah, x1, y1, x2, y2, I can't write, x3, y3, okay? These are collinear if and only if, double arrow, the determinant of x1, y1, 1, x2, y2, 1, x3, y3, 1 is equal to 0. Only way it can be. Now, the test for collinear points can be adapted to another use. That is, when you are given 2 points on the xy plane, you can find an equation of a line passing through the 2 points. Okay?
Oh, so this is what I'm talking about.
Is that what you were meaning? Okay. Yeah. And this is how.
Well, I'll never have to go back and mess with that again.
Right. This time, you just do the determinant of, make the first point your generic point, x1, xy1, and then the 2 points you're given, x1, y1, 1, and x2, y2, 1, and set it equal to 0. If you want an equation of a line through those 2 points.
Wow.
Exactly.
That is
Yeah.
nifty.
So let's do one. Find an equation of a line. Do we have? Yeah, let's just go to the next page. Oops, previous page. All right, clear off this.
Do the DV graph?
What's that?
Or you're just going to,
Yeah. Find an equation of a line passing through these 2 points, 2, 4. Let's see if I can plot the points right this time. And negative 1, 3. All right. Equation of a line going through those 2 points. Okay? Well, what we just saw was then the determinant of x, y, 1. Oh, let me go and plot these. This is 2, 4, and negative 1, 3. Right. Okay? That would be 2, 4, 1, negative 1, 3, 1. Okay? And set that equal to 0.
pretty sure we got to go with the 1s here.
Yeah, because with the x, y in there, it doesn't do you a lot of good.
No, you
So
don't-
let's start with, and it doesn't matter the order of these, so let's start with either the second or the third one, just because I like the variables out front, okay? There's no other reason. So that's a negative position there. Let's start with the bottom one. Let's start with that one and go up, okay? That would be 4x
I like to rewrite it a little more.
Right.
So that would be 3x.
No, start with the bottom one here, and then it would be that.
Oh, excuse me, I wrote the wrong row.
Oh, you could have written them in any order. Yeah,
Yeah,
it still
I just
will
wanna
work,
stick
yeah.
with what you're doing, so
Right.
we can-
right, okay.
So 4x
Yeah.
minus 2y
2y,
times 1, which is redundant.
right,
So there's that one.
yeah. Then let's go next to,
It's negative 1
yeah,
times the 3x plus y, right?
yeah, negative
Negative 1
3x
goes-
plus y, perfect.
Actually, it'd be a minus y, right? Or no, let's see. It'd be a minus.
Minus a minus,
It'd be a plus, and then
A
you
minus.
distribute the negative out.
Yeah.
It'd be a minus again.
minus a minus a minus, okay. Okay. All right. And then we'll have the top one will be
6 minus.
Plus
negative 4
6.
is 10.
plus 4. Right. So what we have here is x minus 3y plus 10 is equal to 0. Or the other way to say that is 3y is equal to x plus 10, meaning y is equal to 1/3 x plus 10/3. Now, the only reason I did that is that slope-intercept form. And sure enough, the slope is 1/3. Tell by the graph, right? Up 1 for 3 across. So it's a positive 1/3. Got it. And then, where does it cross here? Well, it's 1/3 of the way up. That's 2/3. That's 3/3 up. So it's a third. So above that is 3 1/3, which is, of course, 10/3. So, yeah, that works. Yeah, you already have. You paid for the course. Okay. All right. That was example 6. They say they left it in the form x minus 3y is equal to negative 10, which is fine. Nothing wrong with that. Now, that worked. Area of a triangle in a plane.
Oh, no.
Yeah, let's do volume of a tetrahedron in space.
We're really amping it up now.
And I have a feeling we won't do a proof on this one. They do not.
Why? It'd be a lot more in-depth and complicated.
I would say so. Big time. Okay.
That's a,
And they don't put any specific requirements on this, as in the z's have to be positive or the order of the x, y's, and z's, because that was based on our proof with the trapezoids. We're not doing a proof here, so we won't. It would be tempted to try, but let's resist temptation and go on. I'm even wondering if I want to even put points down here, and I guess I will. Okay. This is not a good rendition, but it's the best I can do. But that be the x-axis is equal to y-axis is equal to z-axis. Okay. And then the negative x goes back this way. Okay, and this is negative y, negative z. The volume of a tetrahedron with vertices and these are impossible to draw in here, so why did I even do this? Some x1, y1, z1, some x2, y2, z2, you know, they're just 4 points somewhere in space, non-coplanar, okay, and non-collinear as well.
Can any of them be on the same plane?
None of them can be on the same line.
Not on the same line.
Wait, two can, yeah, any two will be.
Like, I mean on the same plane. Like, can you have 3 points on the plane and then one somewhere else?
Sure. Yeah, I don't think that's a problem.
They can't all be on the same
Yeah,
plane.
what I was trying to say is all 4 can't be coplanar,
Okay.
and no 3 can be collinear.
Right, so that'd be a big triangle.
Right, exactly. So, that's what I was trying to say, okay? So you get 4 points, and why even bother to draw this, because I can't draw them on there. Look at your book. There they are, okay? Then, the volume of this is a tetrahedron. When you connect any 4 points in space, as long as they're all not coplanar, and no 3 of them are collinear, okay? And certainly all 4 can't be collinear.
That'd just be a big line.
Yeah.
What a tetrahedron.
Then, and you just have to take the word for it, the volume of that tetrahedron, volume is equal, again, plus or minus, so you never have a negative volume, and it's 1/6 this time, okay? The determinant of x1, y1, z1, 1, x2, y2, z2, 1, sorry, x3, y3, z3, 1, x4, y4, z4, 1.
This is only for tetrahedrons.
What's that?
This is only for tetrahedrons.
Tetrahedron, yeah. 4-sided figures identified by 4 points.
Okay. So
Yeah, a cube would have to have 6 points, so yeah, it has to be 4.
6. Would it need 8?
Huh?
Would it not need 8?
You're right, 8. Yeah, sorry. There is another shape of 6. 1, 2, 3, 4, 5, 6. Yeah.
So picking the 2 triangles.
Right, or 2 pyramids with
With
a common
lines
base. Right.
Between the corners.
Yeah. Okay. So this is the only one. Okay. Now let's find the volume of one, and let's see if, well, the thing is you have to tick off your 1, 2, 3, 4, 5, 6, 7, 8, 9. I won't need that many. Okay.
Oh man, good luck.
0, 4, 1. 0 on X, 4 on Y, 1 on Z. So it's going to be there. 0, 4, 1. Okay, there's your first point. 4, 0, 0. 1, 2, 3, 4. There's your second point. The next one's going to be 3, 5, 2. 3, 1, 2, 3, 4, 5, 1, 2. Something about like that. These are coming way too close together here. And then your fourth one is 2, 2, 5. So 1, 2, 1, 2, 1, 2, 3, 4, 5. Something about there. Okay? So there's your tetrahedron. Don't have line between those two. There's your base. Yeah. It's a hidden line. I drew it in as if it's visible, but it's hidden. Okay. What's the volume of that tetrahedron? As in, who cares? That would be plus or minus 1/6. The determinant of, why didn't I write in the points? I wrote in 1, but I didn't do it. This first one was 0, 4, 1. The second one was 4, or 4, 0, 0, wasn't it? Yeah. 4, 0, 0,
3, 5, 2,
3, 5, 2,
2, 2, 5. 2, 2,
3, 3 or 2, 2?
2, 2.
2, 2, 2, 5, okay. 2, 2, 5.
It's a pretty 5. It's got 2, 2.
Yeah, okay. Frilly, okay.
Really?
All right, so it doesn't matter really which order, but we'll do them the way they did. 0, 4, 1, 1, 4, 0, 0, 1. This is really slow. There we go. All right. 3, 5, 2, 1. What is the problem here? Okay. And 2, 2, 5, 1. All right. Now let's see. Are you wanting to?
I like the second row, just as it is.
Right. Just leave it like that and go from there. Okay. All right. Plus or minus 1/6. Have to remember that.
On the furthest outside.
Well, let me see. Let me not draw that. Okay. All right.
So, starting from 4.
It's going to be a minus 4. And then times the determinant of 4, 1, 1, 5, 2, 1, 2, 5, 1. And then if you wanted to use our little trick, we could do a 4, 5, 2 here, and a 1, 2, 5 there. You don't like using that, I can tell. What's that?
Just gotta rewrite more.
All right. And then over here, it's going to be a plus, minus, plus, minus, plus 1. So I don't have to write anything. And then this matrix, second, this one would be a 0, 4, 1, 3, 5, 2. This is just going to be our points, right? Or 3 of the points, 2, 2, 5.
You want to augment that again?
Okay, I was just seeing, I think I will. Okay. 0, 3, 2, 4, 5, 2. Okay. Now I'm going to put the line there. Those aren't really determinants because those aren't square matrices, but you know what we're doing. So this will be, I'm going to come up here and do it, plus or minus 1/6 times negative 4 times, okay,
And that would be, you said it would be 8 for the first one?
8 for the first one,
8, 4?
2, isn't it?
Oh yeah, 2, sorry.
Times 2, plus 2, sorry.
Yeah, plus 2.
Okay.
And then plus 10?
Right, is that 25?
25, excuse me.
Okay.
Adding 1 is supposed to be.
All right. And then I'm going to take these lines out because they're confusing to me. Yuck! It didn't take them out. Okay. All right. And we'll do the down slopes. And if I had done my matrix better, that would be a minus 4, right?
Right. 20.
Minus 20,
And then 5.
minus 5.
I just did a minus and then put everything in parentheses.
Right. Now, I happen to look at this and see a minus 25 here and a plus 25 there, and a minus 4 and a plus 8, so that's going to be a 4. So this is minus, that one so far is a plus 6 in there.
Right.
Okay.
Negative 4 times 6 is
Okay. So we'll come back to that in a second. And then we've got to do our other one, plus, and I like this one.
That's
0, and the next one's a 16, and the last one's a 6, and then I'll take these out. Hey, I'm sorry. Okay. Is it 12:15 already? Well, I'm still in class, but it's all right. We're going in person. So, Darlene, right? Is the next room open? Yeah. Or no class in there? Yeah. Nobody's in there. Now watch that door going out into the hall with a lock behind you, so don't pull it all the way through. You can close that if you want to, if you want to do it. Okay. So we did plus 6. And then I was just about to erase. It just won't do it. There it goes. Okay. All right. All right. Minus a
10.
And that's a 0. That's a 60. Minus 60. Okay. So, yuck. Yeah. So these two will make a 6. That's a 12 minus 60 will be a 48. Okay. Negative 48. Okay. And up here we had a 6 minus 24. So add those together and you get a minus 72. And do 1/6 of that. And we'll lose the minus sign, and that will be a 12. Okay, is that the volume?
Yes.
Lost where I am. There we are. Yeah, 12 cubic units, whatever your units are.
Basic.
What's that?
Is it? Okay, it's plus or minus 6, but.
Okay, they left off the plus or minus. I don't know why.
Wouldn't that be a positive 12? Yeah, because they said
Yeah.
12 cubic units in the end.
Yeah, that's the thing.
A negative 1/6.
They should have a negative 1/6 in the solution there rather than 1/6. So
I don't know what negative volume is.
it isn't. Yeah, let's not draw one. Okay. All right.
It isn't, so let's not draw.
Okay.
I can.
Okay. If 4 points in a three-dimensional space lie in the same plane, then the determinant of the formula for the volume of a tetrahedron is 0. So you have the following test, and but I also think that 3 points collinear would do the same thing, but I'm not completely. Well, wait, no, we'll get there.
We're almost done. We got these 2 boxes and then example 8, we're done.
Yeah. And how the time? We got plenty of time? Or?
We got about 30 minutes.
30 minutes. Okay, let's do it. So let's go back to, no, forward. I keep forgetting which is back and which is forward. Okay. All right. Test for coplanar points in space. If you have these 2 points, 4 points, x1, y1, z1, x2, y2, z2, x3, y3, z3, and x4, y4, z4. 4 points in space, and if they are all on in a three-dimensional space lie on the same plane, then the determinant in the formula for the volume of tetrahedron is 0. But, you know, guess what? Okay, I'm sorry. I was saying any 3 points collinear, right? 3 points collinear and the fourth point not collinear, that forms a plane too. So that's
it's what we were talking about.
In either
plane.
case. Huh?
You can have 3 on plane as long as one of them's not on plane.
Right.
That's what we were talking about.
Right.
But
Yes.
if you had more than 2 on line, it would be
Yeah.
a plane or
Right.
just a line.
Yeah, but I was saying 3 collinear points would also have a determinant of 0, but 3 collinear points and 1 not, that's going to be in a plane. So yeah, that's still a plane. So they would all still be, whether any of them are collinear. Well, any 3 or more were collinear or not. Okay. Sorry. Okay. These are coplanar if and only if the determinant of x1, y1, z11, x2, y2, z21, x3, I say x and write 3, y3, z31, x4, y4, z41. If that's equal to 0, then they're coplanar, if and only if. One way implies the other. An adaptation of this test is the determinant form of an equation of a plane passing through 3 points in space. Okay? So if you have one plane going through 3 points, then your determinant, now we only have 3 points, x1, y1, z1, x2, y2, z2, and x3, y3, z3. 3 points in space, they are coplanar if this determinant x, y, z1, x1, y1, z11, x2, y2, z21, x3, y3, z31. If that determinant is equal to 0, you have an equation for the plane. Okay. So, I don't know if we can do this on the graph or not. We'll try. Find an equation of the plane passing through these 2 points, 3 points. Okay. First get my x-axis drawn in here. This is y. They don't. Okay. 0, 1, 0. That would be there. Negative 1, 3, 2. Okay, there's negative 1, 1, 2, 3, 1, 2, right there, and negative 2, 1, 0, 1, negative 2, 0, 1. Okay, those 3 points define a plane. What is the equation for that plane? Okay, that's 0, 1, 0, negative 1, 3, 2, and this is negative 2, 0, 1. Okay, the equation for that would be x, y, z1, 0, 1, 0, 1, negative 1, 3, 2, 1, and negative 2, 0, 1, 1 equal to 0.
Okay. Kind of already started, but what I decided to do first was take negative row 2 and add it to row 3 and 4 and get a couple extra zeros on that last row. Or we could just go off the second row. Let's just go off the second row.
Okay.
Yeah. I didn't see that it had 2 zeros. So just
Yeah. Okay. So this first place here is going to be a positive 1. In fact, the other one's going to be a positive 1 as well. So that determinant would be, let's write what's left. X, negative, okay. X, you're going that way this time, okay. You just do everything to confuse me, don't you? Okay.
We're working with rows now, so you got to think that way.
Okay.
So negative 1, 3, 1, and negative 2, 1, 1. And then the next one's going to be.
Wait. I got something wrong. Ah, I know what I did wrong.
It's a 1 and a 0.
Yeah. This one I messed up. 2, 1. Nope, wait. I got this one wrong too.
The middle one's a 3.
Okay, wait,
Oh,
what?
you already fixed that.
Okay.
Yeah, I changed mine to look like yours and it was messed up.
Okay. All right. I think we got it now. Okay. And let's, just while we're at it, let's take out, this drives me nuts. Okay. Let's just extend again, x minus 1 minus 2, and z to 1 here. And then we're going to do a plus, and that last one is going to be a little easier, x, y, z, negative 1, negative 2 going downward, 3, 0 going downward, 2, 1 going downward, and then repeat that, x, y, negative 1, 3, negative 2, 0. Okay. So let's see what we got.
2x.
2x
Negative 2z.
minus 2z
Negative 1.
minus 1.
I'm just going to do, put that in parentheses, and then I put a minus sign, and then I put the next thing in parentheses.
Okay. However you want to do it, you can do it. Let's do it. Okay. This will be a
Negative 4 times a negative, which will be I'm not doing it, but
okay.
X plus X,
All right.
and then minus.
Okay. And then
Put them together. So that'd be X
wait.
minus.
Okay, I'm going on adding the other. We can. I mean.
I was just gonna put those terms.
Okay. Yeah.
together.
Go ahead. We'll do it both ways.
X minus Z plus 3. And the next one would be 3x minus 4y plus 0 times negative or plus a negative. Negative 12, 0, and a negative. 12, it should have been 6.
Get it or not?
I did.
Okay. Yeah. And that's what the book got to. 4x minus 3y plus 5z is equal to negative 3, or you could put plus 3 is equal to 0. It doesn't matter. All right. If you wanted another application of linear algebra, according to Kepler's first law of planetary motion, the orbits of the planets are ellipses with the sun at one focus of the ellipse. The general equation for a conic section such as an ellipse is ax squared plus bxy plus cy squared plus dx plus dy plus f is equal to 0. So to determine the equation of the orbit of a planet, then an astronomer can then find coordinates of the planet along the orbit at 5 different points and then use those determinants to find the A, B, C, D, E, and F. That looks like such a joy, doesn't it? So knock yourself out. All right. Homework exercises. Any of the odds 1 through 7. Number 9's a proof. 11's a proof. Do either 13 or 15, with 15 being a proof. Kramer's rule, any of the odds 17 through 29, a whole passel of those, or passel and a third. Okay, do either 31 or 33, or both. 35 I would do, and either 37 or 39, either 41 or 43, either 45 or 47, either 49 or 51, either 53 or 55, either 57 or 59, do 61, and possibly 63. And then in the review exercises, again, the odd numbers have answers in the back, and you can do any of the odds 1 through 17, 19 or 21, 23, 25, 27, 29 or 31, 33 or 35, 30, any of the odds 37 to 41, 43, 45 is a proof, 47. And now, here they go, do it again. In calculus, they talk about Jacobians, which are not the followers of King James, but these are two functions, either Jacobian in 2 dimensions or 3 dimensions is what I'm trying to say, and they define them like this, and you can do either 49 or 51. I'm trying to remember, there's something in physics that uses these. Nothing you'll do. You've already finished both physics courses, right? So you didn't run into these, I'm pretty sure. But if you do any, and they may use them in math too, I don't know. But anyway, they're either 49 or 51. You can play with those. 53 is a writing or think through, and 55 is also. Whoa, there's more. Okay. Adjoint of a matrix, 57, either 59 or 61 or both. Do 60. You can do 63 or 65 or 67, 69, 71, and then there's 2 true false that I would definitely think through. Okay? And it says give your answers if not. And then if you are more interested, there's something on stochastic matrices or Cayley-Hamilton theory. I think we've already hit Cayley, and I believe we hit Hamilton as well. Didn't hit them too hard though. So again, those are potential paper topics. And then there's a cumulative test that I don't think you necessarily need to mess with. So we'll start next time in vector spaces, chapter 4. Well, wait, how much time do we have?
14 minutes.
14 minutes to go? Wow, I didn't know we'd finish that quickly. So let me give you the test now. Anyone listening, I can't give you the test now because I didn't get to make copies. I was running late last night. So.
Can I look at it?
Sure.
See if I have any questions or anything on it.
I set it aside so I could run first thing this morning, but all the places were locked up first thing this morning.
On the determinant, that's easy. Determine which property.
Okay.
Okay, so for the property one, do you want?
I'll have to look at it to see. Sorry,
Okay,
I hit the wrong one.
determine which property of determinants the equation illustrates. Would you want us to give the book's name for the property?
Yeah, or anything that's a good enough description. But yeah. If you have a pet name for it that makes sense, that I can follow what you're meaning, I'll take that too.
Call it George.
Okay, right. All right.
Good old George. Work it out, show you that George really works.
Yes. Chapter 4 is talking about vector spaces. And there are several applications that are indicated here by some of the figures that they show here. They don't show something for every section. R sub n, motion in one dimension, well, in n dimensions, or vectors in n dimensions. Vector spaces doesn't have one. Subspaces of vector spaces, 4.3. Yeah.
And unique, you mean unique solutions? So
Single
not,
one,
if
yeah.
it's singular or not, right?
Yeah.
Row zeros, that's what I mean.
Okay. Let me see what you're talking about. Oh, yeah. Yeah, right. If you wound up with.
Just want to make sure.
Yeah. Okay. I've got to remember to make copies of that upon the end of class. So, 4.3 seems to be talking about digital sampling as subspaces of vector spaces. 4.4, image morphing, and 4.7, coordinates and a change of bases, and that's crystallography, which they can do some really weird things with matrices in that, but they can have some pretty crystals.
Yeah, they found, I think they finally found or proven a time crystal or something like that.
I hadn't heard that one.
It has to do with the structures are always changing or something like that. And I've read a little bit about it, not a whole lot, but it was something to the effect of they go on forever.
Right.
Structures.
Right. As in the pattern
Not really sure.
goes on forever, and it just,
It's constantly changing.
yeah, but in a repeating sense or a never repeating sense type. Yeah, I was wondering how that related to crystals. A crystal, when I think of a crystal structure, everything has a place, and it can vibrate and stuff like this, but it has a fixed place. And if it was time, if there was a fixed sequence that it was changing, but it's always going to change in the same sequence, yeah, then that would sort of make some, that would sort of fit, but I don't know if it would or not. So,
I'll see if I can.
that's all right. So let's move to vectors in space. Okay? Now we usually live in 1, 2, or 3 space. We live in 3 space, but we are comfortable in 1 and 2 space. When you get up anything greater than that, I mean, it's hard enough to represent 3-dimensional space on a flat screen. How in the world do you represent n-dimensional space on a flat screen? I don't know. 2-dimensional board, you know. So, in physics and engineering, a vector is characterized by 2 quantities, length and direction, and is represented by a directed line segment. In this chapter we'll see that these are only two special types of vectors. Their geometric representation can help you understand the more general definition of a vector. Geometrically, a vector in a plane is represented by a directed line segment with an initial point at the origin and a terminal point somewhere else, x1, x2, x1, y1, however you want to call it. Okay? And actually the term vector, I didn't know this before I read this book, derives from the Latin word vectus, meaning to carry. Idea if you were to carry something from the origin to a point, x1, x2, then the trip could be represented by the directed line segment. And you want to go according to the vector, which is the shortest distance, the straight line. Vectors are represented by lowercase letters set in boldface type. I can't print boldface, so I put an arrow over them. Okay.
I knew that.
What's that?
I said, there's no way I knew that.
Yeah, exactly. You only had it how many times? Yes. Okay.
Physics 1, Physics 2, Calculus
yes.
3, and any calculus.
All right. So basically, I guess we ought to go to.
And you were right. It changes periodically between like a certain type of thing.
Oh, is that? That's what they meant by it.
The kind of a general explanation is like, imagine if you had a frozen egg.
Right.
It was just sitting there.
Right.
But every 5 seconds, it did a flip.
Right.
So it changes periodically, and they went on to explain where it gets the energy from, and like the top of the egg would be metal, and it whenever it does a flip, it gains potential energy and some other, and it ends up, you know what do they call them? Machines that go on forever.
Rube Goldberg.
Perpetual motion.
Right. Yeah.
Perpetual motion. It's
Right.
almost like perpetual motion.
Right.
Because of its continual gaining and loss of.
Right. Exchanging kinetic for potential energy or whatever, or internal to, Okay, so if we had, say, any old vector there, then this is the origin, this is x1, x2, then we know what we're meaning by that vector. This could be the vector x. Now, that's why they named it that, even though they called this x and this y. The reason they chose x1, x2, they named the vector x. Guess what? There's plenty more letters out there. You didn't have to use that one, okay? But they did, okay? Now, the same, I would have used v. Why not,
For vector.
Yes, exactly.
For u.
Yeah. The same ordered pair used to represent the terminal point also represents the vector. Now, this is what gripes me. In this book, they call this vector x, x1, x2. That looks just like the point x1, x2. In Ron Larson, the trig book, he used angle brackets to denote vectors. Here he uses parentheses. It drives me nuts. I want to still use that because every other text I'm teaching from now uses angle bracket except this one. And he's the same author as one that...
And they are referring to the name of the vector.
Right, exactly.
You would think.
You would think, but he doesn't. So one thing...
But I guess since it could illustrate the point that the vector, the base is at the origin and going out, is the same.
Right. Yeah. But one's a point, one's a vector. The components of a vector are the coordinates of a point. He represents them exactly the same. Okay. Now, if you have two vectors, u and v, where u is, and we'll stay in 2 dimensions and having to use parentheses now, u1, u2, and v being v1, v2. For these two vectors to be equal, their components must be equal in exactly the same order, okay? Though they're not ordered pairs, they're still ordered. Did it to me again. Okay. All right. That means U1 has to be U2, V1, and U2 has to be V2, okay, for two vectors to be equal. That's the if and only if. These two are equal if and only if U1 equal V1 and U2 equal V2. No option there. Huh?
It's a pretty popular band.
Pretty, yeah, right. They are. Were anyway. Are they still? Okay. All right. So let's do example 1. Okay. Let's clear this so we can do example 1. How are we doing on time?
Enough time to do example 1.
Okay. So, to represent the vector U, 2, 3, okay?
I'm just going to keep using
Do it. Huh? I know. I want to do it too. Yeah.
I almost would just say do it.
Yeah. I'll do it. Okay. It'll please me. Okay. So how would you represent this?
Alright, so to represent, okay, what's the question? From the origin to 1, 2, 3, right?
Yeah. Right 2, up 3, and that's your directed line segment. Okay. To the point 2, 3, and this represents vector U, which will be 2, 3. I did it. Okay. All right. Now, to represent the vector -1, 2, what would you do?
Same thing.
Left 1, up 2. There is the vector. I think they call this one V. This point is -1, 2. This vector V is vector -1, 2.
Didn't know we'd be doing such high level math.
Right. Just incredible. And are we out of time now? Huh? We are. Okay. Start next time, vector operations, which for some reason was exactly where we stopped at the last time I taught this course. So I've got my mark there. Let me put this in place. Let me go down and make 3 copies of the thing. Let me turn off